And then question 16 is a probability question. So when Anna shoots an arrow, the probability that she hits the target is 0.3. Each attempt is independent of any previous shot. What's the probability that Anna hits the target for the first time on her third attempt? So she's either going to hit the target, which would be 0.3, or she's going to miss the target, which would be 1 minus 0.3. Let me just have a bit more to press on here. So the probability of her missing would be 1 minus 0.3, which is 0.7. And because they're independent, we can use the AND rule. Okay, so the probability that she hits the first time on her third attempt means she's going to miss on the first attempt and miss on the second attempt and hit on the third. So you are going to be doing 0.7 times 0.7 times 0.3. So non-calculator paper, so we have to multiply those together. 0.7 times 0.7 is 0.49. Alright, so there's 2 digits after the decimal point in the question, so there has to be 2 digits after the decimal point in the answer, times 0.3. So if we do 3 times 49, 9 3s 27, 12, 14. So that's 147. There's 1, 2, 3 digits after the decimal point in the question, so there needs to be 3 digits after the decimal point in the answer. So the answer is 0.147. If you weren't sure where the decimal point went then, the other thing to bear in mind is that probability is always measured between 0 and 1. So it couldn't possibly be 1.47 or 14.7 or 147. It could only be that to be correct. Evaluate whether or not there is more than a 50% chance of Anna hitting the target exactly once. So she's hit it once there with a miss, miss and hit. So the way that we can do this is miss and hit, or she could hit and miss, or she could miss, hit, miss. Now when you're ORing in probability, you're adding them. Now miss, miss, hit, hit, miss, miss, or miss, hit, miss are all going to be multiplying 0.7 by 0.7 by 0.3, but in a different order. But when you're multiplying, it doesn't matter. So the probability of you miss, hitting is going to be 0.147. Hit, miss, missing is going to be the same, or miss, hit, missing will be the same. So it's 3 lots of 0.147. It's up to you what you do here. You can just take that and multiply by 3, or you can add those together. Doesn't matter. I'm spoiled for choice. I don't know what to do. Let's add it. So I got 21, 12, 14, 1, 2, 3, 4. So the probability of hitting the target exactly once is 0.441, which is less than a 50% chance, which would be 0.5. So less than 50% chance. Sean selects 2 balls at random from a box containing 15 blue balls and 5 red balls. He calculates the probability of selecting 2 red balls is a quarter squared, which is 1/16. What assumption has Sean made for his answer to be correct? Right, I'll explain this in a long-winded way. It's only worth 1 mark, and you hopefully would arrive at it more quickly anyway. But if you imagine that we can draw a probability tree out of this, where we've got blue and red, the probability of it being blue would be 15 out of 20, and the probability of it being red will be 5 out of 20. Well, if he's then going to repeat that, the probability of selecting, so 5 out of 20 is a quarter, and that's 3/4. So for that to be a quarter, it means that there still needs to be 5 red balls and 20 balls altogether in the bag. So probability both red would then be a quarter times a quarter, which is what we've got there. In order for that to happen, whatever the first ball was would have to be put back in the bag, in the box, to be drawn out again. If there was 1 fewer ball in the bag, then that probability would change. So what assumption has Sean made for his answer to be correct? That the first ball would be replaced before the second ball was drawn. Okay, if the first ball wasn't replaced, then the probability there would become 4, because there's 1 fewer red ball in there, out of 19, because there aren't 19 balls in the bag anymore. There aren't 20 balls in the bag anymore, there are only 19. So the probability of them both being red would be 5 out of 20 times 4 out of 19, not a quarter times a quarter. Okay, so that's what they were looking for you to arrive at there. So that's it.